Good afternoon, ladies and gentlemen. Thank you for being here with us for today's online event on urban flow modeling and solar forecasting using high-performance computing, partnered with A*STAR's Institute of High Performance Computing. My name is Alethea from the National Supercomputing Centre Singapore, or NSCC for short. For those of you who are not familiar with us, NSCC is a national research infrastructure funded by the National Research Foundation of Singapore. NSCC is Singapore's first petascale supercomputer facility that provides high-performance computer, or HPC resources to all local research institutes, institutes of higher learning, government agencies, and companies in both the public and private sector. HPC resources are beneficial in a variety of ways and in a number of different sectors. It enables research of the highest computational complexity and data intensiveness in areas like advanced modeling and simulation, artificial intelligence, as well as big data analytics for fields like genomics, biomolecular modeling, advanced manufacturing and design, digital twin technologies, weather forecasting, climate research, and quantum computing to be completed in shorter time spans. If you are interested, do find out more about NSCC and HPC at www.nscc.sg. Computational Fluid Dynamics is becoming popular as a virtual planning tool for urban planners to plan the future development of the urban built environment. However, accounting for the detailed urban physics while keeping the entire modeling process simple for the end user is a challenging task. Additionally, solar energy will power 10% of our country's electricity demand by 2030. The limited land space makes it more challenging to deploy onshore solar farms. As such, Singapore is looking into floating solar platforms or rooftop solar farms. Today's talk about urban flow modeling and solar forecasting using high-performance computing will touch on the complexities of the urban flow physics and the role that high-performance computing can play in reducing the computational bottleneck and in solar forecasting. Dr. Harish Gopalan is a scientist in the Fluid Dynamics department at A*STAR's Institute of High Performance Computing. His research projects include IEM Sim, an urban flow, solar, and noise modeling tool, which was selected for the President's Technology Award in 2019. Cloud Sim, a cloud-based urban physics modeling and wind and solar energy for forecasting tool. A client-server software framework for urban physics modeling, coupled mesoscale microscale model for urban flow simulations, and forest management and tree failure analysis using computational fluid dynamics. Before we get started with the talk, please do note that if you have any questions, do post them into the Q&A chat at the bottom of your screen so that Dr. Harish can address and discuss this after the presentation. So without further ado, let me warmly welcome Dr. Harish to get us started. Dr. Harish, please.
Thanks, Althea. Good morning, everyone. Today, I'll be talking about urban flow modeling and solar forecasting using high-performance computing. This is just a brief overview of what I'll be talking about. I'll just give a brief introduction of our department. Then I will give an introduction to urban flow modeling. And next, I will talk about how we can enhance the usability of urban flow modeling tools so that the layman can use it for his day-to-day activities. And finally, I'll briefly touch on solar forecasting. Fluid Dynamics department, we have 4 research areas: coupled and multi-phase flows, computational geometry, design and optimization, engineering fluid flows, and physics-based data-driven modeling. I am part of the physics-based data-driven modeling group. And in many cases, even though it's split into 4 parts, most of us work on interdisciplinary research, which covers more than one of the groups. Now let's get started with the urban flow modeling physics. The image that you see here is a standard image which any atmospheric boundary layer discussion starts with. So this is basically a pictorial representation of the planetary boundary layer. So where we live, that's the surface layer. So the first question is, why do we need to study all these complex processes? All the atmospheric physical processes are coupled together. For example, what happens at the surface layer is driven by what happens above it, and so on. And in terms of why do we need to study it, it depends on the application actually. Say for example, if you're a meteorologist, you would want to study the entire span all the way up to the free atmosphere, because you want to model all the physical processes so that you can predict the weather for tomorrow. Now, if someone wants to study the urban heat island, they don't need to go all the way up to there. Probably they can stop at the capping inversion and study all the physical processes which happen below that. Then if we come all the way to the ground level, if you're interested in the pedestrian level thermal comfort, you need to study only the surface layer. The reason it is split in these different ways is the physical processes and the governing equations and what you can solve depends on which of these approaches you use. For example, if we want to study the entire atmospheric boundary layer, we have to use climate models. There are a number of climate models like the open, widely used open source WRF, which is developed by CCRS, and you have COAMS from the US Navy and ECWMF and COSMOR from the European agencies. So in climate model, you study the entire, all the regimes in there. But so you'll get an understanding of the entire physical processes. But the disadvantage is when you study all the regimes, there is a limitation on what you can represent for certain things. Say, for example, in the climate models, the buildings are represented as 2D drag elements. The reason is because it's so computationally expensive to resolve the detail flow around the buildings. And also in climate modeling, the focus is more on how the surface layer where the buildings are located affects the rest of the atmospheric boundary layer. At the next level, you have the ABL meteorological models. The most common example is PALM-LES. In this case, you study up to the capping inversion. It can model most of the atmospheric physics, including wind, temperature, radiation, and rain, and in some cases, even the aerosol. But it still requires information from the climate model to drive it. Then you have computational fluid dynamics models or models like NVMet, which can do both CFD and some portions of the ABL modeling. So why do we need to go through all these different iterations? The reason is when you look at the climate model, you have like so many equations to solve on so many terms. When we come all the way down to the surface layer, most of those terms are not important. For example, the Coriolis force or the geostrophic forcing, they are not very important at the surface layer. This is the reason, depending on the problem we are interested in, we choose which model to use. So today I will focus on computational fluid dynamics because that's what we have been doing for a while. So in terms of restrictions, computational fluid dynamics is applicable only within the surface layer, and with some modification, you can extend it beyond that. So basically the Coriolis and geostrophic forcing are neglected. And most important thing is the Monino-Bukov similarity theory can be applied. I'll come to what that means shortly. And a typical CFD simulation looks like this. You have an inflow where you specify wind, temperature, and in some cases humidity. You have an upstream region, which is also sometimes called as the fetch region. And then you have the region of interest where you can have trees, water bodies, roads, building. And then you have a downstream region where whatever information is coming out of here has to flow, and then you have an outflow. And in terms of a typical simulation using CFD, the components are, you have the governing equations within the domain, you have the inflow boundary conditions, the wall boundary conditions, the upstream region, the downstream region, and the most important, how do we represent the different structures from buildings to roads? And in terms of the governing equation, I will not go into the details. So we solve for the conservation of mass, momentum, and energy. And because turbulence, we don't resolve it explicitly. We need a model equation for turbulence. And for tree representation, we don't represent it exactly. I will touch on it a little later. And then we have to model the radiation transfer, and if we need gas dispersion and water vapor transport. And also, if we are more interested at the building level, we will go into the building heat and moisture transport. And if the humidity is included and there are a lot of trees in the region of interest, we consider the tree shading and evapotranspiration. And anthropogenic heat generation is basically the heat generated from air cons on automobiles. Those there are no exact equations. So in the sense, the only way we can include them in the modeling is if field measurements are available, we can use them as a heat flux to drive the energy equation. Now, in terms of the codes, the number of these physical processes which are modeled depends on really the code. So depending on what you're interested in, you have to choose which code you want to use. I'll start with the inflow boundary condition. So the inflow boundary condition within the surface boundary layer is specified using the Monod-Nabucco similarity theory or most. So what basically it says is within the surface layer, the wind temperature and humidity can be represented by the equation shown in the slides. Most people who have done the CFD simulations are familiar with the log law. The extra psi terms are basically a measure of the buoyancy effects in the atmosphere. So during the daytime and also late in the night, these terms become important. And in terms of what these parameters mean, U star is referred as the friction velocity, and we calculate it from some reference measurement. And Z naught is a Davenport roughness length. It's a measure of how much drag the surface extracts. For example, the value of Z naught is much lower on the water body compared to the land because the sea surface extracts lower drag on the structures. And L is the Monod-Nabucco length, which is a measure of how much is the buoyancy effect important. And the psi and phi, they are called as stability functions. They have a more or less universal form. And in terms of the wall boundary conditions for wind, turbulence, and humidity, we use same as what we do at the inflow. For temperature, we have to use what is called a surface energy balance. So the equation I have shown here, so basically it balances the incoming radiation with the heat generation due to the buoyancy turbulence, the heat conduction into the building or soil, the latent heat flux if you have a water body, and the anthropogenic generation. Now, one of the problems in many of the CFD modeling tools is the ground heat flux, the latent heat flux, and the anthropogenic heat generation is neglected. In that case, the equation simplifies to what I have shown below. In this case, if the turbulent viscosity goes to 0, the temperature gradient becomes singular. Now, this is a problem which has to be carefully addressed if those other contributions are not included. Now, upstream region, basically we need because for most of the simulation, there is a prescription of what is called as a blockage ratio. It's basically, if you go back to the, so blockage ratio is basically the area of the region of interest to the total area of the domain. The reason this is important is blockage ratios has to be less than certain percent so that your results are not affected by the boundaries. Now, for downstream region, the only requirement is whatever goes down should not be reflected back into the domain. Most of the codes have boundary conditions to actually accommodate that. So we don't have any issues with that. Now the upstream homogeneity is a little tricky because the boundary conditions that we use are approximate. There can be a numerical artifact which can cause the acceleration or deceleration of the wind speed. So if we use the Monod-Nabucco similarity theory, we don't run into that issues. But the most is popular only among the meteorological community. CFD community doesn't care a lot about it. So this issue has been there and it still exists in most of the commercial codes. I show a test case down, which it's called as an ABL homogeneity test. What we do is we specify the inflow profile, and we apply the necessary boundary conditions. So what is expected is at the outflow, because in this case we have no buildings or no pressure gradients or no forcing, whatever inflow velocity we specify has to be observed at the outflow. The second figure, I show the differences in the wind speed when simulated using the most boundary conditions. In this case, so basically neutral refers to when the buoyancy effects are not important. Unstable is the boundary layer we have during the daytime, and stable is the boundary layer we have during the nighttime. So if we use the most boundary condition, we see that the differences in the wind speed, and also I haven't shown here, but even the differences in the turbulence are negligible. The third figure on the what I show is a result, which is a classical result done using the commercial code Fluent. So what they observed is, unless you make certain specific corrections for the wall shear stress, it's not possible to ensure that you have Habier homogeneity. One of the other problems with these corrections is you can't have like a really large upstream region. It can cause acceleration or deceleration of the flow. And in terms of representing structures, buildings are represented as 3D CAD models. The level of details depend on the code. If you use the CFD codes, we can even represent, say, the balconies and everything, assuming you have the computing power to perform all the simulations. The roads and as 2D surfaces. Terrain, in most cases, it's neglected because when you have a terrain, you also have to ensure that the buildings are aligned with it. Now, trees, they are a little tricky to represent because trees, you have trunks, branches, and leaves. It's computationally impossible to represent the leaves. So we use what is called as a porous media model. The idea of the porous media model is basically the interaction between the tree and the wind is just through the forcing. What if we can come up with a simplified model which mimics the drag exerted by the tree on the wind? So that's the porous media model, and that's what is usually used to represent the trees. And shading and evapotranspiration, it's usually not available in most CFD codes. Just to discuss further on the tree, the extra, to represent the effect of the trees, we include this extra drag force term, where the CD is the coefficient of drag of a tree, which is a parameter which has to be specified. The L of Z is a measure of the leaf area index. It basically says how the leaves vary along the tree height. Now, both these parameters are input in the sense the model is static. So once we include that term, the effect of the trees are approximately incorporated. So down here, I show some sample results from our previous project where we simulated the trees in the Jurong Lake district. The first figure on the top left, the trees in there are the actual representation of the trees. The figure on the right is basically how the trees are marked in CFD. The advantage of the porous media model is you don't have to control your mesh size, in the sense if your cell sizes are larger, the trees are marked as bigger, in the sense the drag effects are going to be diffused, but you can still represent it. And the figure on the bottom shows the wind speed at 2 meters. What you can see is in the areas where you see those white patches, basically they represent the drag effect due to the tree. And one other thing which has to be done when you are doing urban flow simulation is the validation and verification part. Now, the first step of validation, which most of us do, is validating with the wind tunnel. Wind tunnel validations are relatively easier because you have precise control on what you specify at the inlet, what is the surface boundary condition, and you can also have a number of measurement points upstream and downstream. But when it comes to validating on the field, it becomes much more challenging. In here, I show an example of a validation we performed as a part of the Cooling Singapore project. The image on the top left is the area around the Robinson Road. So the idea is sensors were deployed and they measured the real-time wind speed, humidity. One of the problems when we are validating CFD is we have to identify the conditions which CFD can simulate. For example, if it rains, we don't simulate that in CFD. So what we did is, the first thing, we analyzed the data and we looked for the what we call as the clear sky conditions, in the sense we picked a specific time of the day, which was 2 p.m. for the month of January, if I'm not wrong. And then we analyzed so the windrows here is from the Marina Barrage. From there, we analyzed the most dominant wind direction. And then we ran the CFD simulations. So at the bottom, I show the comparison of the CFD and the field measurements. So the field measurements, basically, we have included the results from multiple days, because the CFD, we ran it as a steady state solution. We have like only one setup. While in the field measurements, you can have multiple days where you have like very similar measurements. We can see that we are able to match it reasonably well. The next part that I'm going to talk about briefly is the enhancing the usability. So as a part of the development work in the fluid dynamics department, we have been doing significant modifications to the open source code OpenFOAM for urban flow modeling and also for other applications. In here, I'll just touch briefly only on the urban flow modeling part. And this development was inspired mainly from the projects we did for the URA and HDB. So when we did the projects, what we understood was the way we look at things and the way the planners look at things was very different. So we asked ourselves the question, is it possible for us to take all the work that we did and make it available in a simplified form that they can use for their application? And that's how all our new projects have been developed. So in terms of our development work, we have our backend framework, which we call as the Scout core, which is basically all the OpenFOAM modeling enhancements that we add. Then on top of that, we had a Python wrapper, which basically allows us to link to the GUI. And once we have the Python wrapper, we can build a GUI on top of that. I will touch on two of the GUIs that we did recently. So in terms of what do we have in Scout core, in here I touch only on the topics which are specific to what IHPC has done. In some cases, what we created may also have been done by others. It's just that we were not aware of. And when we are confident of the tools that we develop, because all these are developed within the open source framework, we make it available to the public. So one of the things that we are looking at right now is the terrain mesher. For people familiar with OpenFOAM, meshing in OpenFOAM, for terrain, you can do it in two ways, using a snappy hex mesh or a move dynamic mesh. And based on our experiences, we observed that neither snappy hex mesh or move dynamic mesh works nicely if you have like really, really complex terrain. So what we did was we developed what we call as a make terrain utility. So what it does is, within the block mesh frameworks, it adjusts the mesh such that it lies on top of the terrain. This tool is still under development. So once we are confident of it, we'll make it available. The second thing that we were looking at is a surface splitter. So the idea is, for people familiar with shapefiles, when the shapefiles are provided, you get a shapefile for the entire city. So if you want to do the simulations, you convert the shapefiles into STL, you mesh the STL, and you run all the simulations. But in some cases, the city size is, say, for example, Singapore, it's 30 by 40 kilometers. So if you want like really fine mesh near the buildings, there is no way we will be able to do that unless we increase the mesh count to say 800, 900 million grid points. So the idea of the surface splitter is, why not use machine learning to make life easy for us? So what we do is, either the shape files, or if the user provides an STL file, we run it through a machine learning classification technique. In the sense, there are controls on what is the size he wants it to classify. And in certain cases, if he wants to exclude certain buildings, And once we do that, so the image you see on the top right, the color coding basically represents the classification that we did. And once we do that, we can run the simulations. In the sense, there is going to be no difference to like meshing the whole thing and doing it in terms of the results. But in terms of the mesh count, you can reduce it significantly. And another thing that we are working on is what we call as the multi-design solver. So the idea is, for many cases, you have to do multiple simulations where the wind can come from multiple directions. Or in some cases, you have like trees that you want to plant in different areas and study the effect. What if it was possible to do all of them within a single framework? This was the idea for the multi-design solver. This is still in the development phase. And for now, we can support the change in wind speed, direction, temperature, cloud condition, adding or removing trees. And we even have the support for adding or removing buildings. It's just that buildings will not be modeled exactly, but they will be modeled using like immersed body or immersed boundary solutions. And first, I will talk about two different GUIs that we did recently. The first is Scott GUI. This was something we did for the Maritime Port Authority. So the idea here is, when we started the project, we thought, okay, we will do a nice GUI on a Linux system and give it to them. And the MPA personnel said that they prefer a GUI on the Windows system. And for people familiar with OpenFOAM, it's usually well built to run on the HPC system on Linux. Even though there are like Windows built, if we want to run like computationally intensive cases, it's better to run on Linux. So in Scout GUI, what we did is we designed a Windows client which does the pre-processing and user interaction, and it automatically connects to the Linux server and runs the simulation and post-processing. And the network folder we mounted using Samba. So for the user, when he sees us, it's just another network folder on his Windows machine. And the background solver execution and the data transfer was through transmission control protocol. In the sense, the user can set up the case, he can start the simulation, he can shut down the GUI and go. When he comes and reopens the GUI again, the case will either still continue running or it would have finished running. And one other thing that we built into the system was a preprocessor. The preprocessor is not fancy. Basically, it was built so that whatever capabilities MPA wanted within the system for using it, we built into it. In terms of the case setup, it takes less than 10 minutes. So what you do is you load the CAD model, you assign the material properties, then you set up the mesh requirements, you choose your day, time, and input data for simulation. The simulation can be both steady and unsteady. And then if you want gas dispersion, you choose the gas release point, and then you run the simulations. One of the most important work we built into the system was what we called as an intelligent mesher. When it comes to meshing, people, unless they have used CFD or any other computational methods extensively, they are not going to be familiar with setting up the meshing. The idea of this intelligent mesher was, what if we can make the interactions simpler and allow the user to enter the numbers that he is comfortable with and do all the workhorse in the behind. So the way the meshing works is, once the user loads the STL file, based on the size of the STL file, we generate an automatic spacing requirement. And there is a button in the GUI where we have it called as a mesh guide. So using the mesh guide, the user can input numbers and see how the mesh would look like for his resolution. And say, for example, if the horizontal meshing is coarser, say, for example, if the horizontal meshing is 16 meters and the user wants a resolution of 2 meters, all he needs to do is, in the STL refinement box, he has to set a refinement level of 4. So each level of refinement reduces the mesh count by 2. And so the difference between the STL and the gap refinement is the gap refinement refines the mesh only in one direction. Say for examples, if you have a thin gap in a single direction, you can use that. And one of the things that there is no control over is the vertical spacing, because one of the problems is if you need to ensure ABL homogeneity in the upstream region, if you have like vertical refinements, it can cause acceleration or deceleration of the wind. This is just an example of the simulation that we did. So in this case, this is a, you can think of it as a toy problem, in the sense we obtained the HDB building information from the GitHub source. We classified it using the surface splitter, and we just ran a quick simulation with 16-meter resolution near the buildings. The advantages in this case, because of the surface splitting, we could reduce the mesh count to 36 million grid points, and we could even run it on our workstation. And also within the system, we have like some basic post-processing. These are not fancy either. The idea is it will help create all the basic post-processing you need to write the reports. One of the advantages of this post-processing is it will allow the user to post-process big data on his Windows machine. For example, if the case is huge, you can't load it on your Windows machine. But using the post-processor, you can generate the slice of data you need, and you can project it back to the GUI. We are also currently exploring to see if we can use a similar technique on the NSCC to visualize the data. The other project that we did is what we called as a Scout widget. So for some of you may be familiar with the virtual Singapore system. So in the virtual Singapore system, you have both the preprocessor and post-processor. But one of the challenges in there is, how do you run the CFD on that? So the difficulty is that system was not set for running CFD. So what we did is we created a CFD widget of our Scout framework, and we integrated it on the virtual Singapore system. So the CFD widget, it actually resides on a different machine within the A-star framework, and it connects to the virtual Singapore system and runs the simulation. This is something we have in mind for the future, to develop a single web server in which we can mount all our projects. Now I'll touch briefly on solar forecasting. I will just say that we are not experts. We are just beginners in solar forecasting, and Ceres is doing a lot more work. Our idea was to look at solar forecasting from an user point of view, to see if we can create a tool which the user can use. Solar forecasting is important in the local context because we have low wind speeds and there is a lack of space. And also, one good thing which works for us is the abundance of solar radiation. Now, solar energy in Singapore is slowly building up, but once it becomes a more common source of energy, the issues like load fluctuations and need to balance the grid becomes very important. And one of the problems we have in the tropics is the high variability in the cloud movement. And to our knowledge, the commercial solutions, they have not been tested in the Southeast Asian region. So in terms of solar forecasting, you can classify it into three parts: very short-term forecasting, and long-term forecasting. Although the terms are misleading in terms of this is what it is used in the literature. So for the very short term, it's mostly the statistical or machine learning based models. For the short term, cloud imagery or satellite data can be used, which we are not familiar with. And the long term, which we are more interested in, is usually performed using numerical weather predictions and corrections on top of that. So this is just a brief slide of how the climate modeling works. If you are more interested in that, you can attend the next talk in the webinar series, where they will share in detail about all of this. The reason this is important is, if you are interested in predicting the solar radiation, you have to understand the limitations of this so that it can improve the accuracy of the prediction. Now, in terms of solar radiation, we performed it using the open source code WRF. In terms of model choices, you have many different options for the radiation scheme. And microphysics is basically the representation of the cloud and water content and the other thermodynamics within the system. And the cumulus scheme is used to resolve the clouds which are larger than your grid cell. So the first question is, how do we downscale? In the sense, when you want to say run, say WRF simulations in the area around Singapore, you start with a much larger area so that you get the driving physics, and then you narrow it down to Singapore. In terms of the day ahead forecasting issues, based on our limited test, what we observed is there is a systemic bias in the tropical region. And so one of the things which we are looking at, which I think a lot of people are looking at, is a hybrid approach where we get the output from WRF and we use machine learning to correct the predictions. These are some of the initial results that we got. So the WRF we ran using version 4.3. It was a one-way downscaling. So the 81 kilometer resolution, it was run as a WRF global, in the sense we ran the entire world, and we downscaled it all the way up to the 1 kilometer where we cover the Singapore and Malaysia and Indonesia region. And I've just given the settings for the WRF physics that we use. In terms of how long it takes for day ahead forecasting, it took us less than 2 hours on a single node of NSCC. So for, the results I have shown here on the left is the normalized root mean squared errors using the different radiation models. What we see is the persistence models, they outperform the WRF results. Now, this is well known in the literature. Now, the figure on the top right, we show the normalized root mean square error when it is corrected with machine learning. Also, we have included cases where we had the day ahead data, and also in the last case where we had the hour ahead data as a surface feature to calculate the machine learning correction. What we observed is, I think this has also been observed by many people, that the closer you have the corrections, the better you can get in accuracy. So one other thing that we are also looking at is, okay, we have this WRF and machine learning. Once we have some confidence in that, will it be possible for us to create a tool that we can provide that for people to use? So that's the idea behind the development of the SenPy framework in the Scout Cloud. So the way it works is, the user enters the latitude and longitude of his area of interest, and then it creates a database, and he can use it to do like day ahead simulation using WRF. And so it can run in 2 modes. It can run just pure WRF, or it can do machine learning correction if MedStation or real-time data is available for correction. The same thing, it can also be extended to rain and wind farm forecasting. And one of the things I haven't talked about in the talk, so I have to talk about it because that's what the focus of the talk is, the use of high performance computing. In simple words, the more the number of processors, the faster you get the results. I would like to end my talk. I would like to mainly acknowledge 3 folks. Kianvi Lim was the student who tested the first version of our CFD software and provided inputs, especially for developing the Berkeley thermal comfort model. Nigel, he ran all our WRF simulations as a part of his FYP project. And junior college student Shaq, who tested our GUI in his school, and where he was interested in studying what is how the temperature on the building surfaces changes when he changes the material properties of his school. Thank you for your time. I'll be happy to answer your questions.
Thank you, Dr. Harish, for the great and insightful sharing. So I think we've got several questions in the Q&A box at the bottom. Would you like to go ahead to answer those 2 questions first, Dr. Harish?
Actually, the building shapefile data, you can actually, we downloaded it from a GitHub source, which was made available by Felipe from NUS. So it is openly available. The terrain, we didn't use terrain, we assumed it to be flat, and we downloaded the shapefile from OpenStreetMap, and we used our tool to convert it into STL. Selfie, to answer your questions, if you want to find the optimal spot, I don't think this is the tool for that. There are other tools available in the literature which can give you a better answer. And could you explain? Theoretically, so the idea is most doesn't exactly work in the urban area. But the problem is we have a wall function problem, which is well known. So you have an option of either using most and hoping for the best, or you can always go for the sand grain roughness based wall functions. So basically, the way we do it is we implement the boundary conditions, which is consistent with most. So because we run our simulations in open form, we are able to implement it. If you're interested in doing it in, say, Fluent or Star CCM, there are materials available in the literature. You can just drop me an email. I'll pass you the references. People have actually released user-defined functions for doing the same. We cannot handle clouds. We are working on handling the evapotranspiration. Now, precipitation in CFD, we can do it as a wind. If you're interested in wind-driven rain effects, if you're, then we can do. But if you're interested in, say, modeling the cloud microphysics to calculate what is going to be the precipitation, we won't be able to do it. The models, we make it publicly available once we are confident, and also once we make sure, because in some cases the models have like lot of hacks to make it work. Once we clean it and we are confident on it, we can make it available actually. Do we intend to I don't have an answer for that now. If required, we can do it. And the spatial resolution, it depends on how much RAM and how many processors I have. Yes, you can use it to find the outdoor thermal comfort, but just so you know, most of the thermal comfort tools, they have been developed for indoor thermal comfort. So we have to take it with that in mind. IEMs, basically, so basically Scout is our core development, while we have different projects with different agencies. IEM is a tool we built for HDB.
Okay, I think, we have one more question that was asked privately. Are there models or libraries that are compatible with MATLAB?
MATLAB, no, because you can theoretically take this and code it up in MATLAB. It's much easier because you don't need to do any fancy matrix inversion or stuff. It's just that as long as you run a short case, it should be okay. But if you're looking for something fancy, it's better to do it in one of the compiled codes like C++ or Fortran.
Okay, thank you, Dr. Harish. Thank you everyone for all your ongoing questions. So Dr. Harish has shared his email address in the slide, so please feel free to get connected with him after this session. All right. Do also join us for our next webinar, The Crucial Role of Supercomputing in Weather and Climate Science by Dr. Dale Barker from Center for Climate Research Singapore, Meteorological Service Singapore, National Environment Agency, so NEA. And thank you once again to our speaker, Dr. Harish from A-Stars IHPC. And thank you everyone for your time. See you at
Thanks
our
for
next
attending
online
my
event.
talk.
Bye.